GenAI and MLOps Part 25. This episode has 6 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. What is model serialization? Here's a strong way to approach it. Model serialization is the process of saving a trained machine learning model into a file format so it can be stored, transferred, shared, or loaded later for inference or further training. Serialization converts the model, including its learned parameters, architecture, and metadata, into a portable format that can be reused without retraining the model from scratch. Common purposes of model serialization include model deployment, model versioning, backup and recovery, sharing models across environments, serving predictions in production systems. Common serialization formats and methods include Pickle or Joblib for Python-based ML models, saved model in TensorFlow, Torch script or .pt files in PyTorch, ONNX. Open Neural Network Exchange for cross-platform compatibility. Example workflow. 1. Train the model. 2. Serialize and save the model file. 3. Load the serialized model in production. 4. Perform inference without retraining. Benefits of model serialization: faster deployment, portability across systems, reduced compute cost, easy rollback and version management. Challenges include version compatibility issues, security risks with unsafe deserialization, dependency mismatches across environments. From an MLOps perspective, model serialization is an important step in the ML lifecycle because it enables scalable deployment, CI or CD integration, reproducibility, and efficient production serving of machine learning models. Nice. Let's continue. Question 2. Difference between Pickle and ONNX? Here's a strong way to approach it. Feature Pickle. ONNX definition: Python-based serialization library used to save ML models and Python objects. Open standard format for representing ML and deep learning models. Primary use: saving and loading models in Python environments. Cross-platform model interoperability and deployment compatibility, mostly limited to Python. Supports multiple frameworks and languages. Framework support commonly used with scikit-learn and Python. Models supports TensorFlow, PyTorch, scikit-learn, and others. Portability: low portability outside Python ecosystem, highly portable across platforms and runtimes. Security: unsafe if loading untrusted files because arbitrary code can execute. Safer compared to Pickle since it stores computation graphs. Deployment: best for internal Python applications, best for production and multi-platform deployment. Performance: good for simple serialization, optimized for inference. Performance: file content stores full Python object structure, stores model, architecture, weights, and computation graph. Production usage: limited in enterprise production systems, widely used in enterprise AI deployment pipelines. Runtime support requires Python environment, supports ONNX runtime and hardware accelerators. Use case: quick model saving or loading during development. Model serving: edge AI, cloud inference. Interoperability: example, use Pickle when working completely inside Python-based environments. Use ONNX when deploying models across different platforms, languages, or hardware accelerators. Great. Moving on. Question 3. Explain feature pipelines. Here's a strong way to approach it. Feature pipelines are automated workflows used to collect, process, transform, validate, and deliver features for machine learning models during both training and inference. A feature pipeline ensures that the same feature engineering logic is consistently applied across the entire ML lifecycle, helping maintain reliable and reproducible model performance. Typical stages in a feature pipeline include: 1. Data ingestion: collecting raw data from databases, APIs, logs, streaming systems, or data lakes. 2. Data cleaning: handling missing values, duplicates, invalid records, and inconsistencies. 3. Feature transformation: scaling, encoding, normalization, aggregation, or deriving new features. 4. Feature validation: checking schema, quality, drift, and consistency. 5. Feature storage: storing processed features in a feature store for reuse. 6. Feature serving: delivering features to training pipelines and real-time inference systems. Feature pipelines are important because they help prevent training, serving skew, duplicate feature engineering work, data inconsistency issues, manual processing errors. Common types of feature pipelines: batch pipelines for scheduled processing, streaming pipelines for real-time ML systems. Popular tools used for feature pipelines include Apache Spark, Apache Kafka, Airflow, Feast, TensorFlow, Extended Kubeflow. From an MLOps perspective, feature pipelines are critical for scalable, maintainable, and production-ready ML systems because they ensure consistent feature generation, automation, monitoring, and governance across environments. Alright, next question. Question 4. What is metadata management? Here's a strong way to approach it. Metadata management is the process of collecting, organizing, tracking, and governing metadata across data and machine learning systems. Metadata is data about data, meaning information that describes datasets, models, pipelines, experiments, and system activities. In ML and MLOps environments, metadata management helps teams improve traceability, reproducibility, governance, and operational efficiency. Common types of metadata include 1. Data metadata. The exact commands and code are in the written question bank. Let's keep going. Question 5. Explain ML experimentation. Here's a strong way to approach it. ML experimentation is the process of testing, comparing, and evaluating different machine learning approaches to identify the best performing model and configuration for a specific problem. It involves running multiple experiments with variations in algorithms, hyperparameters, features, datasets, architectures, training techniques. The goal is to improve model accuracy, efficiency, and generalization before deploying the model to production. Typical ML experimentation workflow includes 1. Data preparation, cleaning and pre-processing datasets. 2. Feature engineering, creating and selecting useful input features. 3. Model training, training multiple models or configurations. 4. Hyperparameter tuning, optimizing parameters such as learning rate, batch size, or depth. 5. Evaluation and comparison, comparing metrics like accuracy, precision, recall, F1 score, or latency. 6. Experiment tracking, recording configurations, metrics, datasets, and model artifacts. Key challenges in ML experimentation: reproducibility, tracking multiple experiments, resource management, collaboration across teams, managing datasets and model versions. Popular tools used for ML experimentation include MLflow, weights and biases, Kubeflow, TensorBoard, Neptune AI. From an MLOps perspective, ML experimentation is critical for systematic model development, reproducibility, governance, and accelerating the transition from research to production-ready AI systems. On to the next one. Question 6. What is a champion-challenger model? Here's a strong way to approach it. A champion-challenger model is a deployment strategy in machine learning where an existing production model called the champion is continuously compared against one or more new candidate models called challengers. The champion model currently handles live production traffic because it is the best validated model. Challenger models are tested in parallel to evaluate whether they can outperform the champion in terms of accuracy, latency, cost, or business metrics. How it works: 1. Champion model, active production model serving predictions to users. 2. Challenger model, new model version trained with updated data, features, or algorithms. 3. Parallel evaluation, challenger predictions are compared against champion results using monitoring metrics. 4. Promotion decision, if challenger performs better consistently, it replaces the champion. Common evaluation metrics include accuracy, precision and recall, latency, drift resistance, business KPIs, resource utilization. Benefits of champion-challenger strategy: safe model upgrades, reduced deployment risk, continuous model improvement, better A or B testing and validation, easier rollback capability. Common use cases: fraud detection, recommendation systems, credit scoring, ad ranking, real-time prediction systems. Popular tools supporting champion-challenger workflows include MLflow, Kubeflow, Selden Core, TensorFlow. Serving from an MLOps perspective, the champion-challenger approach is important for enabling continuous experimentation, controlled deployment, monitoring, and reliable production model management. Good. Here's another one. That wraps up this episode. Nice work practicing, and see you in the next one.